Okay, section 4 in chapter 13 gets into a lot of chemical reactions, and this is where the meat and potatoes part of the meal is. We want to talk about the preparation of alcohols by reduction. The textbook goes into counting oxidation states and calculating things, and I summarize this whole thing with a very simple statement. Reduction is the addition of H2 to a molecule. So if you've got let's choose methyl cyclopentene here, and we've learned how you can treat this with hydrogen and some kind of platinum catalyst, for example, to give you the alkane. And so what we're not showing here are the 2 hydrogen atoms that you've added to this molecule to convert the alkene to an alkane. And this is a reduction because you're adding H2 to the molecule. Now you can do the same thing for ketones, okay, for ketones. So if you have a molecule like this, and you treat this with hydrogen, and we could use platinum, palladium, or nickel. There's lots of different types of catalysts we've seen before in the class. Okay, so don't get confused if you see nickel in one reaction, palladium in another reaction, and yet platinum in a third. What you're going to form is an alcohol, okay? So this is your ketone functional group. And of course, we know what an alcohol is. And it doesn't look like, it looks like completely different. What's going on there? Well, we're not drawing this hydrogen, and the hydrogen that's attached to oxygen, if we highlight it in yellow, now you can see, oh, those are the 2 H's from the hydrogen molecule that has converted this ketone to an alcohol, okay? So that's a reduction reaction. Now, there are 2 different hydrogen is an awkward thing to handle in the organic chemistry lab. It comes in pressurized tanks. Platinum and palladium are very expensive. A special nickel catalyst is oftentimes very air sensitive and reactive to moisture, and it's awkward to handle. So we oftentimes use very easy to handle reagents, and these come in 2 forms, okay? Sodium borohydride, and I'll draw out the Lewis structures for these so you can see what they look like, okay? So borohydride is boron with 4 hydrogens and a net negative charge. It's got a -1 formal charge on boron. And lithium aluminum hydride is similar, but just different elements. Now, for many purposes, you can use sodium borohydride and lithium aluminum hydride to form alcohols from ketones and aldehydes, but for esters, you want to use lithium aluminum hydride. So this is less reactive. This is more reactive. Okay? It reacts with a lot more functional groups. Both of these are a source of hydride. Okay, so when we use the curved arrow reaction mechanisms, I take a shortcut. Just be aware of that. I just start with H minus, and I use that for my starting arrow to attack something and go from there. We, of course, know that this is not sodium hydride, which is primarily used for deprotonating. We know that lithium aluminum hydride or sodium borohydride are used for reducing, and I'll show you what the mechanisms for that are. Now, sodium borohydride, we write out the formula, NaBH4. For lithium aluminum hydride, there's a little bit more letters there, and it's kind of awkward. So we write LAH. Okay, oftentimes in many textbooks, they use LAH. That stands for lithium aluminum hydride. Again, think H hydride, and I'll show you the curved arrow reaction mechanism and it should be fairly simple. All right, so let's take a look at how these reactions work, okay? That's not going to show up. Let me use a lighter blue. Okay. Reduction of ketones. All right. So a ketone, let's choose, I don't know, acetone here. We haven't talked about the naming of ketones, so don't worry too much about the naming of this. But acetone is nail polish remover. It's a very common solvent for cleaning and drying glassware in the lab. So if I treat this with sodium borohydride in methanol, I can make isopropyl alcohol. Now, how does this mechanism work? It's an ionic mechanism. And what you can do as a shortcut is just draw hydride out here. That's hydride, remember. Okay, and draw those arrows towards the carbonyl carbon. Now, remember that this molecule here has an electronegative oxygen atom. So there's delta plus on the carbon, which is attracted to this negatively charged hydride. And so what you get there is A for attack. You get the alkoxide. And in yellow, I guess I'll draw the hydride I've added. Now that hangs out, but you have a vast excess of methanol present. So there's going to be an acid-base reaction. Okay. And that's going to give you the target molecule. So that's going to be P for protonating. Okay, so when you return an H plus to a alkoxide, you protonate that oxygen and it becomes a neutral molecule. Okay, so you're getting one hydrogen from the hydride, and you're getting another hydrogen from the methanol solvent, okay? So that's where the two H's come from. We're not using hydrogen gas, we're using just, things that you can weigh out and measure very easily, okay? Lithium aluminum hydride can also be used, and the reaction is a little bit different in terms of the steps. Lithium aluminum hydride is extremely reactive. It reacts quite readily with water. So you want to not add it to water. Okay, so step one, add lithium aluminum hydride, let it do its thing. And then step two, very, very cautiously add water. And this will give you, again, just the alcohol. So the mechanism is exactly the same as before. You have a ketone, you have hydride, okay? That attacks the carbonyl carbon as before. And you form a alkoxide in solution here. And that hangs out and stops there and waits, right? And then you add water in a protonation step. And it protonates, okay? So it's AP. I think the other one, yeah, AP. So whether you use sodium borohydride or lithium aluminum hydride, it'll work. Just remember that you have a step one and step two with the LAH procedure. These produce secondary alcohols, okay? So notice the trend. If you have a ketone, you form a secondary alcohol. If you have a ketone that's cyclic, you form a secondary alcohol, okay? So keep that in mind. How about aldehydes and ketones? Aldehydes are just like ketones, except you only have one alkyl group attached to the carbonyl carbon. If we treat this with sodium borohydride in methanol, I'm going to color code my hydrogen here. So you can kind of keep track of what's going on here, right? So remember that the aldehyde already has a hydrogen attached to that carbon. And so here's the hydrogen attached to that carbon. And we're adding 2 hydrogen atoms, okay, across the carbon-oxygen pi bond. One of the hydrogens goes to the carbon, one of the hydrogens goes to the oxygen. And I've highlighted those in yellow so you can see where those are. And if you look at this molecule, you can see that it's a primary alcohol, okay? So aldehydes form primary alcohols, whereas the ketones form secondary alcohols. You could also do this with, I don't know, let's just make it a different aldehyde, just to be creative. But if you wanted to use LAH, remember again, that requires a 2-step procedure. And you form the secondary alcohol. Okay? Count your carbons and just make sure that you're not increasing the carbon count or decreasing the carbon count by mistake. The mechanism is exactly the same as for ketones. The first step is going to be attack. The second step is going to be protonation. Okay? Now let's talk about hydrogen. Hydrogen could also be used. So remember, if you have a something like this, and you treat this with hydrogen and say nickel catalyst, you can form your secondary alcohol. But remember that hydrogen reacts with other things. So if you take a molecule that has a double bond in it, let's say, I don't know, let's put it out here, and we treat this with hydrogen with a platinum maybe or a nickel catalyst, you're going to form, you know, there's going to be mixtures of cis and trans here, but we'll just draw a stick drawing. You'll form the alcohol, which is what you want, but also you'll form the alkane, all right? So remember that this functional group reacts with hydrogen. Okay? Now, if you were to treat this starting molecule here with sodium borohydride and methanol, this will only react with the aldehyde or the ketone to give you the alkene alcohol. Okay, we won't try to name this guy here, but you can see how the alkene does not react with sodium borohydride or LAH. The alkene will only react with H2, okay? So keep that in mind, okay? We call it orthogonality, I can't even say the word, orthogonality of reaction, okay? One reaction will react with just one functional group. Hydrogen reacts with both, okay? So watch out for that when you're looking, okay? Now let's talk about carboxylic acids and esters, okay? A carboxylic acid will react with lithium aluminum hydride. Let's make this a cool looking one. Let's put a 4-member ring there. So if you treat this with lithium aluminum hydride and water, you will form the alcohol, okay? Now, I believe the curved arrow reaction mechanism is shown in the book for this, or some books anyway, and it's highly complex. I don't require my students to memorize it, okay? Just memorize the reaction, don't memorize the curved arrow reaction mechanism, okay? So here's the chemical reaction you need to memorize. Now, sodium borohydride is not a strong enough reducing agent to transform carboxylic acids, which are resonance stabilized, to their corresponding alcohols. So if you were to treat this with sodium borohydride and methanol, there would be no reaction, okay? So remember that as well, okay? So those are the two reactions, or not reaction, of carboxylic acids you need to put on a note card, memorize, become familiar with, okay? Now, let's talk about esters. So that's a carboxylic acid functional group, okay? Carboxylic acid. Esters have this functional group. Okay, it looks like a ketone attached to an alcohol, okay? So you have a carbon that's doubly bonded to an oxygen, and that carbon is singly bonded to another oxygen that has some alkyl group attached to it, okay? And if you treat this with sodium borohydride in methanol, okay, it will not react because the ester, right, if you use those curved arrows to show an additional resonance structure, is resonance stabilized, and sodium borohydride is just too mild of a reducing agent to effect this transformation. But lithium aluminum hydride is very strong. It will react quite readily. If you add excess lithium aluminum hydride, if you're seeing this for the first time, let me define what excess means. That means EXCESS. It's just a shorthand abbreviation. So if we add a lot of lithium aluminum hydride followed by water, what we will get is two alcohols, okay? We'll get an alcohol from this portion on the left, okay? And then we'll get an alcohol from this portion on the right. Let me show you the curved arrow reaction mechanism for this process so this can make more sense to you, okay? But put this down on a note card. LAH will react with esters and you'll get two alcohols. The alcohols could be the same or they could be different. Draw them out, count your carbons, and very carefully think about which oxygen goes with which carbon fragment, and you should be fine. So let's do the curved arrow reaction mechanism for the reaction of esters with hydride. So when you have hydride, we're just going to use H-, okay? And we're going to attack the carbonyl carbon of our ester. And I'll draw it in green there. Now, what happens here is that the alkoxide gets ejected from your molecule. So we're going to take these, lone pairs on oxygen, this formally negative charge, and we're going to swoop in. We're going to reform a carbon-oxygen pi bond, and we're going to kick off alkoxide. So that's called E for the elimination step, okay? So I'm color coding the hydride green so we can see why you need excess. Now here we're forming an aldehyde. Aldehydes react with lithium aluminum hydride and it's present in excess amount. So clearly hydride is going to say, oh, an aldehyde, I know how to react with you. It's going to attack the alpha carbon or the carbonyl carbon, and it's going to form an alkoxide, okay? So you're forming, it's a double reduction, right? You're forming two hydrides there on that same carbon atom. And that hangs out, that's step one. Lithium aluminum hydride makes this alkoxide and it makes this alkoxide. And then what happens is you drip in water very cautiously because it explodes, it reacts very violently with lithium aluminum hydride. And so what that's going to do is protonate these alkoxides. So we'll draw that reaction here. When you add water in step 2, this is going to pick up a proton and give you this alcohol. And we'll draw that reaction over here as well. Step 2, you're adding water to your mixture of alkoxides, and that gives you an alcohol. Okay, so those are your 2 alcohol products from the reduction of this ester. Okay, it's kind of an intricate series of events. It's A, E, A, and then, you know, you have protonation down here at the bottom. Okay, so the overall sequence for this is A, E, A, P. There's so many letters there that might not make sense to you, but if you wanted to make a note card and memorize the mechanisms, you could write AEAP, and maybe that could help spur you or prompt you to construct these curved arrows for the reaction mechanism. Okay, so that's a little bit about the reagents. All right, let's do a problem. All right, now that we know about lithium aluminum hydride, sodium borohydride, and hydrogen, and how they reduce or react with some or all or none of aldehydes, ketones, esters, and alkenes, let's do problem 12 here in the textbook. So it says to draw a mechanism. I don't want to do that. I don't have enough time to do that, but I'm going to predict the major product, and you can listen to how I'm rationalizing through this, okay? So what we need to do in part A here is to analyze what molecule we have. We have what's called an aldehyde, and we're treating this with lithium aluminum hydride. And I know I'm going to have the same number of carbons, all in the appropriate branching and so on, but I'm just going to change that double bond to a single bond and make an OH. It doesn't matter if you draw the OH going up or bottom right, it doesn't matter, okay? How about in B? B is a ketone, so same thing. I'm going to change that doubly bonded oxygen to a single bond and rewrite the O as an OH. I'm not going to do anything with those 2 aromatic rings on either side of the molecule. Okay, but I'm going to be sure to draw in those double bonds there, okay? In problem C, we have sodium borohydride and methanol. And remember, that's a selective reagent for ketones and aldehydes. This is a ketone, so that is the functional group that's reacting. It does not react with isolated double bonds off to the side of the molecule. So I'm going to rewrite that molecule and change that double bond oxygen to a single bond oxygen and write OH. All right, so for problem C, I'm going to write OH there, okay? Now, it is possible that I form the R isomer and the S isomer from this reaction. Remember that the aldehydes and ketones are planar. They're sp2 hybridized carbons that are flat, and the hydride can attack from the top face or the bottom face of the molecule, giving you an OH that's either a wedge or a dash. But I'm not going to draw the racemic mixture here. Here is an aldehyde in part D, and we know that alkenes do not react with lithium aluminum hydride, so we're just going to write the alcohol that forms from this. We want to make sure that we have the same number of carbon atoms, and here, instead of drawing the OH pointing up, I'm just going to point it pointing to the bottom right. For E, this is where it gets a little bit more complicated. We have an ester. And here you need to analyze the 2 sides very carefully, okay? So in blue, we have all of these carbons here, okay? So I'm gonna change that carbon-oxygen double bond to a carbon-oxygen single bond and write the O as an OH. And then I'll switch to a yellow color here. I have an oxygen with 2 carbons, and I'm going to split that off the molecule. So that's ethanol, and I'm going to write that like this. So in part E, we have 2 alcohols that are formed from this single reaction. In F, we need to be very careful. Okay, this is sodium borohydride we're using. Sodium borohydride is a mild reducing reagent and will only react with ketones and aldehydes, not esters. So it's going to react with this ketone that's right here, but it will not react with the ester on the right-hand side of the molecule. So to draw the products, we're going to modify the aldehyde, okay, to write the secondary alcohol that's produced there. But the ester, since its resin is stabilized and sodium borohydride is just too mild of a reducing agent, it will leave that ester intact, okay? All right, so that in a nutshell is this section, section 4 of the chapter 13.